Hello, so this is the second video in the Algebra 2 series. Today we'll be going over functions and quadratics and polynomials. So we're going to get through quite a lot. So let's just start off with a function. So a function is something that has a domain and a range. The most important thing about a function is that there is a single input that produces a single output. So in other words, a function can be anything like this, so that each x value there's a singular output value. However, some things are not functions. So for example, x equals 1. And you'll notice the reason why this is not a function is because at every single point, for the x value x equals 1, there's an infinite amount of output values. So one way that we can test whether something is a function is the vertical line test. So the vertical line test is essentially take a vertical line at every point in the function, and if it passes, then it's a function. So like this guy passes the vertical line test, but if I did this doesn't pass the vertical line test. Because if I draw a straight line here, there's two outputs that go to a single input. And that's one of the most important things about a function. Okay. So, yeah. Let's actually practice a little bit with domain and range. And I'm going to introduce a little bit of notation too. So let's say something like this. So let's find now you may be wondering, how do we do this? Well, you pretty much just add the functions together. So you literally just get, but the x squareds cancel, right? So you just get 4x minus 7. That's what that is. Now we can do the same thing. And if you actually do a subtraction, you'll get negative 2x squared minus 4x plus 17. Let's try something different. Let's try, it's an F. Okay, this gets a little complicated. Not really, but I'm actually going to factor the bottom, and you'll see why in a second. Now let's say we want to find the domain of this function. Well, the domain is every single x value that I can plug into this thing. I can plug in everything except for 2 and negative 6. Because if I plug in 2 or negative 6, that makes the bottom 0, and we can't divide by 0. So our domain is going to be that's how we can write domain. Now that was a little bit of an introduction to function notation. And now I want to introduce you guys to what happens when we do something like this. All these little coefficients and stuff, not coefficients, all these little numbers, they transform the function. Or yeah, so I'll show you what each one does. So this guy is what we call a vertical shift up, pretty much. So in other words, it just shifts the graph up by or down by whatever k is. This is a horizontal shift. This is a horizontal stretch or horizontal shrink. This is a vertical stretch or horizontal shrink, or sorry, a vertical shrink. So, if I were to have some f of x, let's say it's at the origin, and I did this, I would actually move to the left by c units. So, it'd be like this. I hope this is review. If you were to have, let's see, f of x plus k, that would shift up the graph by k. And then a and b are just going to either make the graph like this or wider. So if you were to make b greater, then it's actually going to shrink it. If you were to make it less, that's going to widen it. However, the reverse is true for a. If you were to make it bigger, then the graph will get wider. And if you were to make it smaller, it'll be like that. That's pretty much how transformations affect the function. And so I'll show you how to identify transformations. Let's say this is the parent function. And let's say g of x is transformed such that this is true. And by the way, the 2 is outside of the cube root. So we'll say because this is in front, we have a vertical stretch by 2. There is a horizontal shrink by 2. And then because of that, we're going 2 up. That's pretty much all you need to know about transformations. Actually, hold on. There's 2 more transformations you need to know. If this is the parent function, then this guy is a reflection across the x-axis, and this guy is a reflection across the y-axis. And if you end up having both, then you get a reflection across the origin. I hope this is just review. These should not be like full-on lessons. These are kind of just practice problems. So I really hope that you know that. If not, there are other supplemental resources that you can find to help you. Okay. Now I want to get to the idea of composite functions. So composite functions are a little bit interesting. So a composite function is when you plug another function into another function, if that makes any sense. So you can represent a composite function like this, or sometimes it'll be this little bubble. I'll show you what this means essentially. It means that at every point I see x, I'm just going to plug in m of x. So k of m of x composed of m of x is just going to be 6 over x over 6 over x plus 5. And then just clean it up, multiply it by x over x. So that just becomes... Okay. And then if we wanted to find the domain of this, we're going to find where the bottom cannot equal 0. So our domain would be And actually, you know what? I made a bit of a mistake. So our domain would normally be this. However, I forgot to check something. I forgot to check that the domain of m of x, you can't plug in 0. So we actually have to include that as well. Because how is this thing going to be defined if our input is not defined? So if m of x is not defined, then we also have to include that into our domain. I apologize. That's my bad. Okay. Now I'm going to get into one more thing. I need to find a practice problem for this, actually. And this is the idea of inverse functions. So an inverse function is exactly what you think it would be. Or at least pretty much what you would think it would be. So an inverse function is essentially the reverse function. So if a normal function, you plug in x, you get y, right? Or you get f of x. An inverse function is you plug in y and you get x. And I'll show you what this actually means. A really important thing is that if you compose a function and its inverse together, or an inverse and its function, doesn't really matter. They're inverses of each other, so it doesn't matter. You just get the input, x. And we will actually use this later on, but finding inverses, pretty simple. And I'll verify this with you in a second. So, let's say we want to find the inverse function of 2x squared minus 1. I'm going to write this as like this. Okay. To find the inverse, we just switch x and y, because that's potentially what you're doing. And then you solve for y. So you get x plus 1 over 2, and then square root. And this is the inverse function of f. I said that if you were to compose the two, then you would just get x. So let's try that. Let's compose f of the inverse function that we just found. So that would equal, if we plug in this for x, that would equal 2 times square root, Plus 1 over 2 squared minus 1. Okay, 2 times x plus 1 over 2 minus 1. And when you look at that, we get x. This essentially proves that these two are inverses of each other. Okay. Now I'm going to move on to graphing quadratics. I'm going to do two examples, and then I'm going to do some examples of polynomials, just general polynomials. So let's say we wanted to graph the quadratic x minus 1 squared plus 3. Okay. First thing I'd actually do is use transformations. If you know what x squared looks like, then you should be able to get this pretty easily. This is a horizontal shift by 1 and a vertical shift by 3, so the vertex is now going to be here. And then I just like to plug in a point next to it. It's like 2. So if I plug in 2, I get 4, right? An important thing about quadratics is that they have something called the axis of symmetry, and that's where the vertex is. So on this axis, points are symmetric. So what that means is if at 2, this is equal to 4, then at 0, the function should also equal 4. So it just becomes like this. And we're done. Let's say we have a quadratic in the form of this. Okay. If you guys remember the formula for the x coordinate of the vertex is negative b over 2a. In this case, that means the x coordinate of the vertex is at 2. So let's figure out what the y coordinate is. F of 2 should be equal to 6 minus 8 plus 4, which is 2. Okay. So the vertex is at 2, 2. Great. Again, we're going to do the same thing. Plug in 3. If you plug in 3, you get 9 minus 12 plus 6. That's equal to 3. And then again, we're going to use the axis of symmetry. So if at 3, this is equal to 3, then at 1, it should also be equal to 3. So there we go. Okay. Now we're going to get into polynomials and graphing polynomials. So let's say I want to graph something like this. The best thing with graphing polynomials is using something called end behavior and the roots. So I'll make this simple. So if you were to FOIL this out, you'll notice that we get a positive x to the 5th. We'll get a positive odd polynomial. So a positive odd polynomial looks something like this. It's going to be negative infinity as x is going to negative infinity, and as x gets bigger, it's going to get bigger. So that's what's going to happen with this. Then we just use the zeros to guide us. So we have a 0 at negative 4, we have a 0 at negative 3, we have a 0 at negative 1. So an important thing to note is if the zeros have odd powers, that means that the function is going to pass through at that point. So I'll show you what I mean. So because this is an odd power, it's going to pass through. It's going to pass through here. It's going to pass through this. And it's going to look something like that. That's a rough sketch. But yeah. Let me show you another example. And I'll show you what I mean. What happens with an even power. So we want to graph something like this. Well, first we factor. Okay, now we have two odd power things. So I'll show you what happens now. So the end behavior of an even polynomial is going to look like this. It's going to go Oh, and it's also not negative, so you don't have to worry about it. If it was negative, it'd be like this. And if the odd was negative, it'd be like this. But since this is positive, it's going to be this guy. So we have a root at 0 and we have a root at 3. So I'll show you what happens. So it's going to look like this. And because it's an even power, we're going to do something interesting. It's going to bounce off the roots. And it's going to do the same thing at 3 because it's also an even power. It's going to look exactly like this. Okay. Now I want to get to long division of polynomials. So let's say I want to find this guy. Well, we just use long division. So to do that, we just see how many times x squared goes to x to the fourth, goes to x squared times. Then we multiply times these guys. That gives us okay. We do the same thing. How many times does x squared go into x squared? One time. Oh, wait, what? Sorry, how many times x squared go into x cubed? X squared, or x times. And then we just do it one more time. How many times x squared go into 6? 6 times. And 12 minus 5 is 7. So. And then this is the remainder. And then, so, this is the answer we get. That's all. And this is just long division from numbers adapted to polynomials, pretty much. Now I want to show you a different type of division, and it's called synthetic division. So synthetic division is a little bit weirder, and essentially I'll show you what you do. So you're going to use the coefficients of pretty much the top, and then I'll show you what happens. So whatever makes this guy 0, which is 2, we're going to put that here. We'll use the coefficients of the top guy. So coefficient of x to the fourth is -1. Coefficient of x cubed is 0, of x squared is 0, of x is 90, and then we have to include a constant term, which is also 0. So all we do is we bring down this first number, we multiply it, and then we add. We do the same thing. -4, add, multiply. Okay, 82, multiply, 164. Now, these are just the coefficients of the thing that we're going to get. So, -x cubed minus 2x squared minus 4x plus 82 plus 164 over x minus 2. It's pretty easy. which is pretty cool. I think it's pretty cool. So yeah, that's how you do it. That's how you do synthetic division, how you do long division. I think it's pretty cool. Or I think synthetic division is pretty cool. But yeah. I think that's it for the video. That goes over polynomials, and that goes over quadratics as well. And I'll see you in the next one.